that as we read the book or any other book related to this subject, you suggest that we scrutinize the mathematical treatment in it or just jump to its conclusions?
To the mathematical treatment. I mean, you are being graduate students. I mean, you are almost graduates. Next year you will be graduating. You should be able to do the mathematics. So you should go over the mathematics also.
Scrutinizing it, just getting the general idea?
No, doing it in detail. You have to be able to reproduce that calculation. If you cannot reproduce it, ask it in the class. And about your questions in the class, you can basically ask anything. I mean, if you don't understand the paragraph, you can ask it. If you just ask all the paragraphs, I will basically continue lecturing. The important thing is that you ask the questions. Even if it's purely mathematical. If I think that it is too long to discuss in the class, I will just let you know and then just hand out a detailed derivation. So you should ask anything that will help you understand the material. No restrictions.
So on Wednesday, the first lecture, the first hour, on this, I don't know if you went through the step where the book uses Z substitution.
The Z substitution?
Yeah, so you use Z as R double prime minus R prime. And then when the substitution is done to the integral, now one of the integrands, one of the terms, is not explicitly dependent on the variable integration. So then it takes it out. Is this valid?
Yes.
But Z is dependent on R double prime, which is the variable integration.
Well, you see, for example, if you have integrals of this form, so the oops. The integrand depends on both of the variables, right? Now, one thing you have to pay attention to in these things is what are the limits. So let's say overall space. Then I can make this change of variables. I can just define the delta vector to be r prime minus r double prime, so that this d cubed r prime, f of r prime minus r double prime, this becomes, well, in this integral, r double prime is a constant. So this is nothing but d cubed delta f of delta. Now I can put it back inside, d cubed r double prime, d cubed r delta, f of delta. Now this is equal to d cubed delta, f of delta, d cubed r prime, r double prime. Well, we might have some other factors over here.
It feels like cheating.
It
feels like cheating. How do you justify this?
Well, you see, the problem is in here, the integrand seems to be a function of r double prime, but actually it is not. So that's how we can justify it. You see, look at this one. Let's look at this example. dx 1 over x minus x prime squared plus, let's say, some constant squared, alpha squared. It looks as if it depends on x prime from minus infinity to infinity. It looks as if it depends on x prime. So what is this integral? It is just, we have such a function. This is the location of x prime. This is the total area below this curve.
But here, x prime is a constant. Because
No,
it's
I
a
mean-
single integral.
Now, you see, this can be inside an x prime integral. F of x prime. We can be having such a part. Now, that x integral only is basically the area below this curve. And as I change x prime, it's only the curve shifts, but the area below it is constant. So that x integral is actually independent of x prime. So that integral we can just take out of the x prime integration. And since it is independent of x prime, you can either make a change of variables, say that x minus x prime is some other variable y, which is actually just shifting the origin of your x coordinate. Or you can say that since it is independent of x prime, just pick a value for x prime, let's say 0, then the value is that one. So that's what the book does in a couple of places.
Then, when we finish the first iteration, the first integral, the second integral will take the result of the first integral in terms of x prime.
What do you mean by first integral, second integral?
The inner integral.
Okay, the x integral is, we evaluate it, we see that it is not a function of x prime, so we can take it out of the x prime integration.
X can be taken out of the x prime. We don't have a term for epsilon. We don't have a term for epsilon in this system. But x minus x prime
Okay.
have x prime in it.
Okay,
Okay. So, and it has also x in it.
okay.
So it has, the integration has to be, both integrations should be done over it. It
Should
can
be?
done over this term.
But, I mean, eventually you do the integrals one by one. So I do the x integral first. The result is independent of x prime. Then I need to do the x prime integration.
The result independent of x prime.
Oh.
I'm not integrating over x prime, but the result depends on x prime as a constant.
No, this integral doesn't depend on x prime as a constant. This integral is independent of x prime. It appears in the integrand, but the result is independent of
Okay,
x prime.
So which means that this trick is not always valid. Only when the value of the integral does not depend on the constant of that integral, which is not a
Sure.
constant for the other integral.
Sure. And if you can eliminate that dependence on x prime by a suitable change of variable, that means the integral is independent of x prime. But it is also crucial that you pay attention to the limits. Because when you are shifting your integral, you are changing the limits. So if the limits are finite, then okay, you can eliminate the x prime dependence of the integrand, but then the limits will be x prime dependent. And hence the integral will be x prime dependent. So only if the limits are infinite, you just shift them by x prime, let's say. Infinite shifted by x prime is still infinite. Now just to review what we had done in the first 2 days of this lecture. We were looking at the macroscopic electrostatic fields. We were defining them as an average. And the last thing we obtained was we could write the potential of our system corresponding to this average electric field as phi of r was equal to d cubed r prime rho of r prime over r minus r prime. This was basically, we put some charges in the system. And this is the potential created by the charges that we had placed explicitly. Plus, there was a correction to this term which we could write either in the form d cubed r prime, the polarization density, dot with r prime hat divided, no, r minus r prime divided by r minus r prime cube. So this was basically due to the, I mean, when you put some electric field in your, if you take your medium, put it in an electric field, or put some charges which create these electric fields, you will be polarizing the medium, meaning that you will be moving the charges in the atoms and molecules slightly. The nuclei will slightly move in the direction of the electric field, and the electronic cloud will move slightly in the opposite direction, creating local dipole fields. This polarization field P at the point R, we had defined it, if you remember, we were taking this averaging volume and we were integrating, we were averaging the dipole moment. One over V prime, where V prime was a volume around this point R, and this is the dipole, average dipole moment relative to the point R. So that's how we define this polarization. And then we had said that, okay, this additional term, we could actually write it as a, like the first term, with the identification that it corresponds to a, let's call the bound charge density, which was minus the divergence of this polarization density, and the surface bound surface charge density, which was nothing but the normal component of this polarization density. So if we calculate the corresponding electric field, minus the gradient of this phi, and take its divergence, in the bulk at least, this will be equal to 4 pi rho. This is the charge that we actually placed, plus rho b, the charge corresponding to this polarization, the bound charge. But this rho b is nothing but minus the divergence of this polarization. And if we just reorganize the things, we see that the divergence of electric field plus this 4 pi polarization is equal to 4 pi rho. Rho is the charge we put, so that is the one we are actually controlling. The other one, P, depends on the properties of the material. That's not really under our control, but of course we can study the properties of the material and try to obtain P as a function of E. And that combination over here we defined as D and called it the displacement field. Now, P in general in a material will be a function of the electric field. Of course, there are exceptions. It will always be a function of the electric field. There are exceptions. And for most materials, for not so large electric field, it will be linear in the electric field. Now, of course, you can just imagine this as a kind of a Taylor expansion in terms of the electric field. This polarization will be a function of electric field, and hence you can expand it. And if the electric field is not very strong, you can ignore the higher order terms. If the material is homogeneous, isotropic, then the polarization vector will be in the direction of the electric field, etc. So this is in a sense, the first approximation where chi E is called the susceptibility. It basically measures how susceptible the matter is to polarization. And then this D field just becomes 1 plus 4 pi, the susceptibility, times the electric field. The displacement field is also now proportional to the electric field. And this proportionality constant is called the permittivity. Basically, it measures how much electric field does the material permit to be in it. Well, this was basically all we did. We said that we proved that it was possible to write the potential in this form, and then we made these identifications, and now we define that instead of the polarization vector, we define this displacement field vector. And so in linear dielectrics, at least, the displacement field is proportional to the electric field, so you have to take that into account. And if you remember, the last thing we did was this example of we had two dielectrics, epsilon 1 and epsilon 2. We had a point charge over here, and we had seen that in this configuration we have to somehow modify the method of images. We can still use the method of images, but we have to modify it for region. Let's say this is region 1, region 2. In region 2, basically the system was equivalent to a system of the plus charge plus the image charge, and we had seen the image charge was again positioned symmetrically, and this image charge was equal to epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 times the real charge. So at least we also recovered the known limits when both mediums are the same. There is no boundary. So in region 2, there shouldn't be any image charge. There's only a single charge. Image charge doesn't form. So if you see epsilon 1 is equal to epsilon 2, there is no image charge. Furthermore, if the region 1 is a conductor, which can be treated as a system in which the epsilon 1 is infinite, and when epsilon 1 goes to infinite, the image charge is just minus the real charge. And then in region 1, the potential created was the same as the potential created by a single charge at the position of the real charge. And this Q double prime was twice epsilon 1 divided by epsilon 1 plus epsilon 2. Q. Again, if we take the limits that we already know, when epsilon 1 is equal to epsilon 2, that is, there is no boundary. In region 1, it will see the real charge, so that is Q. So once we know the charges, we can even identify the charges. Once we know the potentials, we can calculate the electric field, and from the electric field or the discontinuity in the electric field, we can calculate what is the surface charge density at this interface. Of course, it will be a bound surface charge density because we didn't put any charges in the interface. Now your questions. Well, basically we did everything in chapter 5. No, I did everything in chapter 5. So any questions about chapter 6? Yes, Anil, your first question. You already have questions in your pre-reports, so you can even ask them.
In chapter 5, I have one question. I have about the polarization type of one of the polarization type.
Orientation polarization.
Polarization. It was written.
Chapter 6.
It was written. There was no polarization in orientation. Polarization was kind of changed. That kind of sentence written. I just didn't understand.
So, what is orientational polarization?
The molecule is already dipole, but then each molecule has its own orientation and completely random between them. But when you apply an electric field, the orientation changes so that it opposes the electric field. So that creates the polarization.
So why there is no polarization in orientation polarization?
Why? Can you repeat the question?
Ask him.
Why there is no polarization in polarization? In orientation polarization.
If there is no electric field, then the positions are random. So that's why there's no polarization. If there is an electric field, then there is a polarization.
Is that what you were asking for?
As far as I remember, there is an electric field and there is no polarization in the orientation polarization. External field, there is a polarization.
Yes, the charge is symmetric with respect to the nucleus of the atom.
Mm-hmm.
And then there is no odd multiple.
Okay.
And there's no dipole. Then the orientation doesn't matter.
Okay. So
So if that's the kind of or particle or molecules,
that there is no orientation polarization in that case.
in that case.
Okay.
So that's a case where we don't have. I guess that's
Which case?
if you have an atom, just an atom, you have something spherical, where the distribution does not resemble a dipole, then the orientation doesn't matter.
That is his second question, but not the first one. So what does he mean? Let's first understand what he means. So basically, this is why you need to be a bit more detailed in your questions, all of you. So that when you need to ask them again, you don't need to go over the chapter. Well, the idea is, you see, how do you polarize a material? We said that, okay, when you put the material in an electric field, the negative charges are slightly displaced in the opposite direction of the electric field. The positive charges are placed in the direction of the electric field. But if you look at the single molecules, well, we have molecules that don't have any dipole moment, like, for example, CO2. If you imagine the carbon dioxide, it's a linear molecule with carbon at the center and 2 oxygen atoms at the ends. Now, I don't remember which one is positive, which one was negatively charged. I think the oxygen was slightly negatively charged. The carbon was slightly positively charged. So if you consider each one of the bonds, they have a dipole moment. But there are 2 dipole moments in each bond, and one is pointing in this direction, the other one is pointing in the other direction. So it turns out that they cancel each other since the bonds are identical. The carbon dioxide side has no electric dipole. But if you put this in an electric field, it will shift the electric charges depending on the direction of the electric field and create a net dipole moment. So this is usually called the polarization. That is probably the polarization you mean in your question. Now, there are other molecules, like water molecule. We have the oxygen over here, hydrogen, and hydrogen. Oxygen will be slightly negative, oxygen will be slightly positive. So this system has, each bond has some polarization, has some dipole moment. But since now they are not pointing in opposite directions, the sum will not be 0. So the molecule as a whole has a net dipole moment. Now, if you put this in an electric field, well, the potential between a dipole and an electric, of a dipole in an electric field is minus E dot P. So the dipole will try to align with the electric field. So this molecule already has a dipole, which will try to align with the electric field. So you have this water, if you just pick up a glass of water, it won't have any net dipole moment, the glass, because all the molecules are randomly oriented. One of the molecules has a dipole moment in this direction, the other one has in this direction, the other one in that direction, so net dipole moment will be 0. But if you put it in an electric field, the dipole moments will try to align in the direction of the electric field, and hence there will be more molecules aligned in the direction of the electric field. So you obtain a net polarization in the direction of the electric field. Furthermore, there will be a polarization. I mean, when you put the water in an electric field, I mean, it's not that the system will rotate as a whole without any changes. The charges will also be displaced. Their configuration in the molecule will also change, creating a polarization, an additional polarization. So even in orientational polarization, there is polarization. But you see, this polarization, due to the reconfiguration of the charges inside the molecule, is done against the electric field of the nuclei. And the electric field of the nuclei is usually huge. So this kind of polarization will be much smaller than the orientational polarization. Most of the time it will be neglected. So that's why probably in the book it says that there is no polarization. Actually there is. There will always be. But it will be probably small compared to the orientational polarization.
Each molecule is a dipole, then should create an electric field around it, which should align the other dipole accordingly,
Sure.
creating a net polarization,
Sure.
even without an electric field.
Well, let's see. We had already seen how 2 dipoles interact, right? we have seen that most of the time if you have a dipole here, another dipole over here, they will align. They will try to align. But the problems are, for example, problem is the atoms are not really at rest because of temperature. So they are constantly rotating around where they are constantly moving around, etc. So they don't really have this fixed position. So there are two possibilities. Either this random motion is too strong compared to their tendencies to align. In that case, you don't get any spontaneous polarization. In the other case, this tendency to align might be much stronger than thermal effects, thermal vibrations, etc. In that case, you do get this polarization. And the materials that can be polarized by themselves without an external electric field are what's called the ferroelectrics.
But this means that if I cool the water, if I get ice, then I should get some polarization.
Well, even in ice, okay, the atoms don't have translational motion, but they still have vibrational motion. So if you think like this, and ice is just a close pack of atoms. Imagine Girai sitting next to you. You cannot stand up. Neither Girai can stand up. But you can just vibrate in your position and hit each other.
Yeah, my orientation will remain the same.
No, not necessarily.
I think this is tunneling, right?
No, this is not tunneling. This is just rotation. Rotation is easy most of the time. It's easy for atoms to molecules to rotate, changing the orientation of the dipole moments. And even for ferroelectrics, I don't know if water is a ferroelectric at sufficiently low temperatures, there is a temperature at which the ferroelectric property disappears. But in magnetic systems, I mean, this is more common. Every magnet is what we call a ferromagnetic material. They have a magnetic dipole moment. And they can align, and once they align, they will stay there, they will become permanent magnets. And once you heat it above the Curie temperature, they just lose their magnetic property. Magnetic dipole moments will be randomly aligned. When you cool them down, they don't get spontaneously magnetized. What happens is you get these very small, these regions, I mean, even in a ferroelectric, that is probably what you would get. Just imagine this. This is our ferroelectric material. They will try to align. So this dipole moment over here will try to align with this dipole moment over here. It can be an electric dipole moment or a magnetic dipole moment. At the same time, this dipole moment on the other part of this material will try to align with the neighboring dipole moment. But this other dipole moments are far from the first dipole moment, so they don't really know what is the orientation of the other ones. So they will just align among themselves. And if you look at some dipoles over here, they will also align kind of randomly. And they will kind of try to push the nearing dipoles to align with themselves. So these regions, if you imagine this as cooling from a high temperature, where first there's no alignment, then as you cool the temperature, they try to align, but each domain, so-called Weiss domain, just aligns independently, and they grow, these domains. But eventually, these domains will, these regions will collide. You see, there will be this region oriented with this orientation. There will be this other region with such an orientation, and other regions, etc. So each one of these will have their own orientations.
With sharp boundaries.
At least in the magnetic case, yes, the boundaries are quite sharp. Now then, when these boundaries, if you consider a dipole in this boundary, let's say at this point, should it align vertically with one of the domains, or should it align with slight angle with the other boundary? It doesn't really have too much of a preference. So just by chance, let's say, it just chooses one and stays there. But then it doesn't have any any influence that forces it to align with the other domain. Then the thing is stable. We have all these large domains. Each one has its net polarization, but the system as a whole is not polarized because each one of these domains are randomly oriented. Then you apply an external electric field, let's say. So you have this system, this ferroelectric material, which has zero net polarization. Of course, it is made up of domains which has net polarization, but as a whole, it has zero polarization. So let's say you apply an electric field in this direction. Now that dipole in that boundary now has a preference to align with the external electric field, which is also the electric field of one of the neighboring domains. So even if it was initially vertically aligned, now it will rotate. So in the presence of external fields, the domains that are already polarized in the direction of the electric field will grow, whereas the other domains will not grow, will get smaller, will shrink. So the system acquires a net dipole moment. Now you remove this external electric field. But again, the dipoles at the boundaries now has no preference to go back to their initial orientation. They stay where they are. So your material is polarized even though there is no external field. So of course, for these materials, you cannot just say that the polarization is proportional to the electric field. It is not valid. Other questions? Yes, Rosa. Come on, you have questions in your pre-reports. You wrote them, right? So why don't you ask them?
What are these field electric and fiber electric?
Yes, what are they? Do you know them? Have you ever seen a piezoelectric material?
Yes.
Where?
Physics 251.
251.
First document.
Out of the physics department, let's say, have you seen a piezoelectric material? Out of this physics department, out of any physics department? Let's say in your kitchen.
Probably is.
Where?
İngilizce'nin de bu soğuk su buharı üreten şeyler var ya.
No.
Soğuk su buharı, onların içine varmış.
Probably.
İşte bizim patlatmamız.
There's more common one. If anyone of you is smoking, you are constantly using one, probably. Hmm? Hmm? Lighters. You see when you click some of them, there is just this spark. So that is created by a piezoelectric material. So if you compress a piezoelectric material, it creates a large electric field. So what happens in the lighters is that you are basically compressing a spring, and once the spring is compressed beyond the critical limit, there is a mass that is released with the spring, and it hits this piezoelectric material, compressing it.
Also the bedroom scales. Bedroom scales also can be
Yeah, that
change it
probably.
to measure scale.
Now it works both ways. If you try to change its dimensions, it creates an electric field. If you apply an electric field, it changes its dimensions. So for example, if you want, in the labs, if you have these microscopes, for example, most of the time, if you need to adjust the position very precisely, let's say in electron microscopes, you need to adjust the position of your tip. In the electron microscopes, you basically have a conducting tip moving along the surface. And you need to be really precise. I mean, there are a couple of approaches. One thing is, one possibility is you just adjust the height of your tip such that there is a constant current running through it. There is this tunneling electron microscope, so as you scan the surface, you move your tip to make sure that the current is constant. And if the current is constant, you model that the distance between your material and the tip is constant. So if you know how much you move your tip to keep the current constant, you know the variation of the height on the surface. And to control this vertical motion of the tip, you use a piezoelectric material. You apply some electric field to the piezoelectric material. It changes its size, so you can control the tip. That's another application of the piezoelectric materials. Pyroelectric materials, if I'm not wrong, they do the same thing. I mean, piezoelectric materials are basically sensitive to temperature, to pressure. Pyroelectric materials are sensitive to temperature. So you apply a temperature, it creates an electric field. For example, people are trying to create cold fusion using pyroelectric materials.
What's the relationship?
Well, what you need to do in cold fusion is that you have to make sure you have to collide the nuclei. So you somehow have to accelerate them and they hit each other. Well, how do you accelerate nuclei? You create an electric field, but you need a very strong one. You shine laser to this pyroelectric material. Inside you create small cavities where you can put your deuterium, let's say. And if you can create large enough electric fields in these cavities, well, they will accelerate the deuterium. They will collide, and if they collide fast enough, you get fusion. Of course, nobody succeeded it for the time being, but there are people working on it.
Can you give us an idea about the working principle of piezoelectric pyroelectric?
I don't know, to be honest. One possibility is that, for example, hypothesis, let's say they are made up of atoms that are not symmetrical and have some molecules that are not symmetrical and they have a permanent dipole moment. So if you apply an electric field, you are basically trying to change their orientation. And it might be that, I mean, you see, if you have two very flat objects that have dipole moments, let's say in this direction, so they will be very flat. If this is the direction of their dipole moment, somehow they create a dipole moment in that direction. If you apply an electric field in this direction, they will rotate, they will try to rotate. But as they rotate, they will be pushing each other away, hence changing their direction, size. This is a hypothesis which should be tested, studied, etc. Other questions? So, yes, Jihad.
Is there any relation between the dielectric displacement and refractive index?
Displacement field and the refractive index, there will be when we study.
We know that there are materials which less than 1 refractive index.
You mean less than 0?
Complex numbers there, examples. So, is it possible for the electric displacement?
Well, we will see what does it means to have a complex refractive index and a complex dielectric constant. But not yet. I mean, it will make more sense when we study the dynamics. So basically what will happen is this epsilon, the dielectric constant, and hence the refractive index will be a function of the frequency of the applied electric field. A complex dielectric constant basically means it's a conductor. It also conducts electricity. And the relation between the refractive index and the dielectric constant is approximately the square root of the dielectric constant is your refractive index. I'm saying approximately because the exact relation is this dielectric constant or the permittivity, electric permittivity multiplied by the magnetic permittivity. And for most materials, mu is approximately 1. Those we will study. To define the refractive index, we have to define what light is first. Yes, other questions? You can ask any questions about any of the material we have covered.
I'm asking the charge density of not regular shapes, like a paraboloid, so it's conductor. I couldn't able to define surface mathematically.
You mean a paraboloid?
Maybe the other shape doesn't matter. Maybe the other shape, paraboloid also.
So this is the shape, right?
Yes. It's a conductor.
The surface. Well, what's the expression for a parabola? In this case, z will be equal to x squared, right? in the simplest form. This is your paraboloid. This is your surface.
No, if it's a conductor.
So this is the expression for the surface. Okay. I didn't say whether it's a surface, whether there's anything there, or it's just a...
It's simple here, but when you get to the charge distribution, it will cease to be simple.
Of course, it will cease to be simple, but he asked for the formula, and it is simple, of the surface. Now, then the problem is, how do you obtain the surface charge density? So how do you create that surface charge density to start with? You put this in an external electric field, or what do you do?
That's the charge inside.
A charge inside. Okay, so you have this parabola, you put a charge somewhere over here, so what will be the surface charge density? That's your question.
Not a single charge.
Hmm?
Not a
Yeah, I
single-
mean, if you can solve for a simple single charge, you can just superpose for many charges.
So it's a paraboloid with no end, then we can say it's grounded, right?
Is it grounded? I don't know. I mean, did you ground it?
It's
Well, if it goes to infinity, it's...
Surface charge density.
But he can fix it to non-zero potential. If he doesn't do anything, that means it will be grounded. But he can fix it to some other arbitrary potential if he wants. Let's say grounded. So how do you solve such a problem?
And then when we look for the green function, where the boundary is zero, has potential of zero.
And this is the green function. The solution of this one is the green function. So we are actually looking for the Green's function now. So if we can solve this problem, we can solve an arbitrary potential on the boundary. But first we need to solve this problem and obtain the Green's function. How do we solve this problem?
On the outside of this parabola, we take an image charge.
You take a?
Image charge.
Will that work?
Very practice.
Hmm?
Very practice.
And try,
Hmm? You can try.
maybe a line.
Well, I'm not so sure a single line image charge will work in this case. Now, what's the definition of a parabola?
I think it was that the distance of every point to a surface is equal to that to a specific point.
Well, basically a parabola, as you said, it should be something like this. You just take, it has a focal point, and if you just, this distance and this distance, they are equal for every point on the parabola. Does it help? Not really. I don't think you can put an image charge. Then what? Okay, we learned about the Green's functions, but first we have to obtain the Green's function to solve a problem. So we have to obtain this Green's function, which is the potential of a point charge. We cannot use the method of images. At least I couldn't come up with a simple image charge distribution which will be suitable. Now what?
I have a feeling, intuition that calculus of variation can help. But I don't have a clear idea about that.
Well, you see, at this point, most of the time, you just try whatever you can. You want to do calculus of variation? Great. If you can formulate it, fine. What I would go for first would be I would just look at all the coordinate systems that are known. So, for example, if there is a coordinate system in which, let's say, we define the row coordinate as the square root of x squared plus y squared, the phi coordinate as tangent of phi is equal to x over y. This is just like the cylindrical coordinates. But let's define the third coordinate. Let's say u is equal to z minus x squared plus y squared. If we can come up with these coordinates, of course you have to, will they be orthogonal to each other? Probably not. And you have to write the Laplacian in these coordinates, and the Laplacian in these coordinates, you have to see if it is separable. You can try the separation of variables. If it is separable, you can apply the separation of variables, then the solution will be kind of quite easy. Because your boundary is, the equation of the boundary is u is equal to 0. So that's a simple boundary. I would probably first go for this. Hmm? Well, then we have the Laplacian. If it is separable, this is a simple boundary. We can impose boundary conditions here. And of course, you need to separate your volume, your domain into two parts. Probably this will be another domain. Inside that surface, outside that surface, your potential satisfies the Laplace equation. And solve it, the Laplace equation, in that dashed volume and out of that dashed volume. And on the boundary you have a surface charge. Just match the potential at the surface using that surface charge, and you know the potential. If this coordinate system doesn't work, we'll see if there's something else, some other coordinate system which will give you a simple boundary equation.
But if we separate the volume like this, what is the boundary condition?
Well, you see, you have zero boundary, zero potential here. This is one boundary condition. The other boundary condition is that your potential should be continuous across this surface, and its derivative perpendicular to that surface should be discontinuous, at least at that point. Just like we did when we were proving the addition of spherical harmonics. There wasn't actually a surface there, but we just imagined the surface and calculated the potential of a point charge using separation of variables in spherical coordinates.
So then we have to solve for the two volumes simultaneously.
Yes. You see, solving the Laplace equation is easier than solving the Poisson's equation. So you try to convert your problems into Laplace's equation. And of course, Laplace equation and Poisson's equations are not the same equations, but in a sense, you are kind of patching the solutions of the Laplace equation across the surfaces that contain the charge. And once you do this patching, you have the solution of the Laplace Poisson's equation. Yes, Abdul, do you have any questions? Everybody asks.
Not up to date.
Any questions about any of the things that we had done up to this point? Not necessarily about this week.
Can I ask about the homework?
Sure.
About the third question?
Which is
Sorry.
the ellipsoid. Okay. So you have.
That's right, it's volume charge density.
Okay, so let's see. The surface charge density was given as Q
Over
for ABC, x squared over a to the 4 plus y squared over b to the 4 plus z squared over c to the 4 raised to the power minus 1/2. Hmm? 4 pi. Okay. So this was the surface charge density. The ellipsoid equation of the ellipsoid was this one. This is equal to 1, and you are supposed to find the total charge. And what else? The field.
just outside the surface.
Well, the field just outside the surface is nothing but sigma. 4 pi sigma. In the normal direction. Inside there is an electric field is 0. We know the discontinuity in the electric field. Outside the electric field should be perpendicular, and we are done.
How can we know that it's symmetric?
Hmm?
Real direction.
Well, it's a conductor, right? So if it's not in the radial direction, it's the normal direction, perpendicular to the surface. And on a conductor, it has to be perpendicular to the surface, on the surface of the conductor. So basically, at least this part of the problem doesn't require any computation at all. So we are done. Now the other one, the total charge, showing that Q is the total charge, is the part that is complicated. Because the total charge is sigma ds. Now what is ds?
dA over the angle at the surface.
Which is?
The unit
No, you see, ds is, let's say, r squared d omega. But anyway, these won't be in use to you. You have this complicated surface. Now what?
project it onto x bar plane
Then?
and find the relationship between dA and ds. The
Great.
coefficient.
How do you find that relation?
ds over ds is equal to dA over cosine angle between the normal of dA and ds, and that angle can be cut from the dot product between the gradient and the k direction.
Not bad.
Is that not, that's much easier.
Hmm?
Doesn't change our computation. It's simple.
Well, let's see. I like another way. Let's look at the vectors. We have the vector A, we have the vector B. What is the magnitude of A cross B?
A times C times.
So this is A times sine theta. So what is the area of this parallelogram? Area is equal to the magnitude of the cross product. So great, we have a way of calculating the areas, if we can identify vectors. So this is our ellipsoid. So we take a patch over here, which corresponds to, let's say, a rectangular region over there. Now, if we can calculate this vector and also this vector, let's call them V1 and V2. If we can obtain V1 and V2, then in fact ds vector area vector will be nothing but V1 cross V2. Now this is the expression for the surface. Let me just consider two nearby points, x, y, z, and x plus dx, y plus dy, and z plus dz. They are both on our surface. So what is the change of x squared plus a squared plus y squared plus b squared plus z squared over c squared as you go from one point to the other one? How much does this combination change?
Gradient, dot product with
Well,
dx.
let's start with this doesn't change because we are on the surface. On the surface, this is just 1. Now I will be writing the gradient. On the other hand, I can write this differential in terms of x, y, z, dx, dy, dz as, no, this is 0, sorry. 2x dx over a squared plus 2y dy over b squared plus 2z dz over c squared, this is equal to 0. So if you'd have any 2 points on the surface very nearby, x dx plus y dy plus z dz over a squared over b squared over c squared, this should be equal to 0. Now let's calculate V1. Let's take, this is dy, this is dx. So we have this very small patch on the xy plane. And I want to calculate the very small, corresponding very small plate area on my surface. Now V1 is along the edge of this patch over there. The corresponding side, this side dy, along that side x doesn't change. So dx is equal to 0. That point V1 is equal to, well, basically 0 in the x direction plus dy, let me call it 1, in the y hat direction plus dz, let me again call it 1 in the z hat direction. This is what V1 is. So V1 basically connects this point to this point. Of course, for the special final point in which dx is equal to 0. And dy1 and dz1 should satisfy this relation because those 2 points are close to each other. So whenever you have 2 very close points, they should always satisfy that equation in the rectangle. So what we have is dx is 0, the first term is 0, so y times dy1 over b squared plus dz1, no, sorry, plus z times dz1 over c squared should be equal to 0. So that tells me that, let's say, dz1 is equal to minus c squared over b squared y times dy1. Now dy1 is just dy basically. So v1 is dy in the y hat direction minus c squared over b squared y. Now here we have a z also, y over z dy in the z direction. This is my v1. I will basically do the same thing for v2. V2 basically corresponds to this side where the y coordinate doesn't change. So dy is 0. So v is dx2 in the x direction plus dz2 in the z direction, since dy is equal to 0. And again, we have this relation between those dx, dy, dz. But this time, dy is 0, x times dx 2 over a squared plus z times dz 2 over c squared. This is equal to 0. So dz2 is equal to minus c squared over a squared x over z times dx2. So we now know what v2 is also. v2 is equal to dx in the x direction minus c squared over a squared x over z dx in the z direction. Now we have our v1 and v2. We can construct our surface vector v1 cross v2, which is equal to, well, both of them are one is proportional to dx, the other one is proportional to dy. So the s vector will be proportional to dx dy, which is, as your friend has pointed out, it's nothing but the area on the xy plane. So what is the cross product? Let's see, y cross x minus z. Y cross z hat is x plus, so let's see, minus c squared over a squared x over z in the x hat direction. So we are done with the first term in v1. So z cross x y, so that is minus c squared over b squared y over z y hat, and z hat, that is 0. So this is our ds vector. Now let's write the ds magnitude. This is equal to dx dy 1 plus c squared over a squared x over z, no, c to the 4, a to the 4, x squared over z squared plus c to the 4 over b to the 4 y squared divided by z squared, everything square root. Or this is dx dy divided by z squared times c squared, x squared over a to the 4 plus y squared over b to the 4 plus z squared over c to the 4 to the power 1/2. Now let's say sigma ds is q over 4 pi abc dx dy c squared over z squared. That complicated square roots, they just disappear. And then you need to evaluate this integral. Yeah, still it won't be a very trivial integral, but nevertheless much simpler than what it looks like. because all those square roots, now they are gone. Well, if I were you, I would just make a change of variables. I would just set, let's say, dx is equal to a times u, dy is equal to b times v. Then u squared plus v squared, now this is u, is equal to something like 1 minus z squared over c to the 4, some z squared with some coefficient. So it looks like a sphere now. Yeah, in fact, if you make the change of variable, z goes to a t, now it will be a sphere in u v t coordinates. So you are basically integrating over a sphere in these new coordinates.
I tried to do substitution other than writing area elements. That time that doesn't help.
Hmm.
Here it should be z, not z squared, right? That's why I don't have it.
Now it says z squared. Here you mean? Well, let's see. Yes, it's the z. And you see sigma ds is equal to q over 4 pi ab c over there dx dy divided by z is c times square root of 1 minus x squared over a squared minus y squared over b squared. And c's just cancel. If you make that above change of variable, this just becomes q over 4 pi ab du dv divided by square root of 1 minus u squared minus v squared. Just make one more change of variable. Just define rho is equal to square root of u squared plus v squared, and tangent phi is equal to u over v. Sigma times ds just becomes q over 4 pi ab. No, sorry, ab also cancels. There are no ab's because dx is a times du, etc. And you end up having rho d rho d phi divided by square root of 1 minus rho squared. So if you integrate q over 4 pi, well, the phi integral just gives you 2 pi rho d rho over square root of 1 minus rho squared. Rho goes from 0 to 1. And that integral, now these 2 pi's cancel, q over 2. That integral is just square root of 1 minus rho squared with a minus sign, rho from 0 to 1. And you end up having q over 2. If I didn't make a mistake of 2 somewhere, the total charge is q over 2. Now the trick is how to calculate ds.
This is only for the top surface.
Yes, this is for the top surface, he's right. Because z is equal to this one for the top surface, z is equal to minus that one for the bottom surface. So the charge, this is the total charge in half of the ellipsoid. Above the xy plane. By the way, this calculation of the integral and the surface area can also give you hints on how to obtain this charge distribution to start with. Because you see what we did. By making these change of variables over here, we map the problem to a sphere. On the sphere, you can do separation of variables. So just do these, exactly these change of variables in the Laplacian. Well, of course, it won't be so trivial because the Laplacian will have these coefficients A, B, C now, but you can give it a try. Or you can just look up the definition of elliptical coordinates and do separation of variables in elliptical coordinates. Yes, Jihad, you still have a question that you didn't ask.
Can you solve also the fourth question?
Which one? What is? Which is?
Two cylinders.
Hmm? Two cylinders. So we have these two cylinders, plus V0, minus V0, and you are supposed to find the electric field everywhere. Let me solve a question in your previous homework. You remember you had this two infinite wires plus lambda minus lambda. You remember this? And you were supposed to show that the equipotential surfaces were cylinders. Hmm? Hmm? It was? One way?
One wire. He said one wire.
One wire. No. There were two of them. It should be your previous homework. Let's solve this one. Now, if you calculate the potential everywhere, you get lambda over.
In this homework, the first question has both cylinders coaxial.
Mm-hmm. Concentric. Are you sure?
Yes.
Give me the
And
question.
then potential also the surface also has a charge.
No, this.
Given.
Oh, okay. So this is a different problem.
And somehow a sphere fits completely in between two of them.
Okay. So this is the question in your new homework. Sorry. Okay, so not this problem. So we have these spheres, cylinders, and here we imagine a sphere, and you were supposed to show that the integral of the potential over this over the volume over the surface is equal to V of R. Right? So what is V? V of r prime. So let's see, what are the charge densities? It was plus lambda and minus? No.
Not given.
Nothing is, no, it's not set, it's not given a name.
Okay, I don't care.
Sigma
Lambda.
1, sigma 2.
Sigma 1, sigma 2. Okay. So V of r, it will be sigma 1 times 2 pi a. This is the linear charge density times the logarithm of, let's say, r prime over rho prime over a. No, r prime. This will be the potential. Now r prime is square root of x squared plus y squared. So this is our potential at the point r prime. You have to evaluate this integral. So your problem was calculating this integral. You have to evaluate this integral of the logarithm of r prime over this sphere.
My problem is the first one, A.
A. Calculate the potential everywhere. Choose the potential at the axis of the cylinder to be 0. So what is the electric field inside the inner cylinder? Inside the electric, it's 0. So the potential here, which is 0, is also the potential here. So on the surface of the cylinder, the potential is 0. Now the electric field in this region, what is the electric field? For example, we can use the integral form of the Gauss's law if you like. So we just, let's say this is, these are our cylinders. I can imagine a cylinder of this shape, let's say of radius r, then E dot ds, since the electric field is radially out, E dot ds will be just height h. This will be E times 2 pi r h. On the other hand, this will be equal to 4 pi times the total charge enclosed. Well, the total surface charge density is sigma 1, and the total surface within our cylinder is 2 pi a times h times sigma 1. So the 2 pi's cancel, h cancel, and we end up having E is equal to 4 pi a sigma 1 over r. So this is the electric field between these cylinders. Now let's calculate the potential, let's say between this point A, at the point A. Now the potential at the point A minus the potential at the point r is equal to 0, which is 0, will be equal to minus from the 0 to Ra of E dot dl. This will be equal to minus 4 pi a sigma 1 over r times dr. Well, from the 0 vector up to the distance a, the electric field is 0, no contribution to the integral, so the lower limit starts from a to the distance of the point r. So the potential at the point Ra is minus 4 pi a sigma 1 times the logarithm of Ra over a. Well, let's say where did we derive this divergence of electric field is 4 pi rho, right? So the integral of E dot ds, which is 2 pi r h times E, that is 4 pi times 2 pi a h sigma 1. So 4 pi is in the numerator. Now let's see, let's take the point B. Let's evaluate V of RB minus V of, let's say, R, the magnitude is equal to B. The potential difference between the surface of the outer sphere and the point RB. Now, because I basically know that the potential at the surface of the outer sphere is nothing but minus 4 pi A sigma 1 logarithm of B over A. This one I know. I will use this one. So this will be equal to some point on the outer sphere in the integral from that point to RB minus, well, the electric field will have basically the same form, but the difference will be 4 pi over R1 R times A times sigma 1 plus B times sigma 2. Because if when I imagine my Gauss surface, it will both contain the inner cylinder and also the outer cylinder. Dot dr. So we just evaluate that integral. V at RB is equal to minus 4 pi A sigma 1 logarithm of B over A minus 4 pi A sigma 1 plus B sigma 2 times logarithm of RB over B. Which we can also write as minus 4 pi A sigma 1 logarithm of RB over A minus 4 pi B sigma 2 logarithm of RB over B, which is nothing but the superposition principle for the potentials. The first term is the potential created by the inner cylinder. The second term is the potential created by the outer cylinder.
Here I try to answer your question about whether the potential at infinity will be zero. So I try to take the limit as r goes to infinity.
You cannot set the potential to zero at infinity.
I expected to find something finite, because that's the physical case. If we shift the potential at some point, we also shift the potential at another point by a finite amount. So it's not zero, it's some other number. But here it's divergent.
Well, you see, shifting is fine, but once you know that the differences are finite, you can shift everything. Here, what this tells you is that the potential difference between infinity and a point not at infinity is infinite. So you cannot really, if you set the potential at infinity to a finite value, then the potential at every other point is infinite. So you should better not set the potential at infinity to a finite value. It should be infinite so that the potential in the region that you are interested in will turn out to be finite. So this is one of the examples where you cannot set the potential at infinity to be zero. Another example is the infinite plane. You cannot set the potential at infinity to zero. Well, of course, not being able to set the potential at infinity is not really a physical case, because at infinity it's away from all the charges, and hence you should be able to set it to zero.
Also,
Infinite plane is not physical. So basically that's the problem. Infinite plane goes up to infinity, so the assumption that there are no charges at infinity is not correct anymore. Now, for any localized charge, eventually if you are far away enough, it will look like a point charge. That's what the basis of the dipole expansion is. And since it looks like a point charge, the potential at infinity will be 0 for any realistic localized charge distribution. Any last questions?
Is there a way to write charge density without trial and error?
Without?
Trial and error. So I have the charge density in Cartesian coordinates, let's say. I want to write it in spherical coordinates. So what I try to do is that I put it in the integral, volume integral, and modify the expression so that it gives me the total charge Q.
For example, give me an example.
Let's say a line.
A linear charge then,
Yeah.
along the z-axis.
Yes.
Some thickness? Some thickness or infinitely thin? Well, you see, the question is, what is the Dirac delta in various coordinates? So that is, I'm afraid, the easiest way is to do the trial and error. So what do you mean by this function? Well, in this case, it will be, let's say, Dirac delta of x and Dirac delta of y. Well, if you want, what you can do is this lambda, what you can try to do at least, this is equal to lambda times x is nothing but r sine theta cosine phi, and then Dirac y is r sine theta sine phi. But, well, that's it. How do you simplify this? Well, this is also a valid expression in spherical coordinates, by the way. You can use this expression if you want.
What if we have a non-uniform distribution?
Along this line? Well, that you are saying that lambda depends on z. Then this is equal to lambda z is nothing but r cosine theta.
So how do you normalize this?
It is already normalized. Oh, if you want to write it in this form, lambda r cosine theta, Dirac delta of sine theta is either -1 or sine theta is +1 with some coefficient a. So is that what you want? No, sorry, sine theta should be 0. Sine theta should be 0.
The above expression.
Hmm?
I didn't understand the above expression. So here we have
Which one? This one?
the Dirac delta argument.
This one? The argument over here?
Yes.
Well, in spherical coordinates, x is equal to r sine theta cosine phi, and y is equal to r sine theta and sine phi.
So basically it's just sine
Hmm?
basically it's just sine theta. Left.
It should be sine theta.
So now
Of course, with some coffee constant now. Then you need to determine that constant A. Or,
it's going to turn out to be a constant. Are we sure that?
no, it's not a constant. I'm not sure.
So again, it's triangle. That's the method.
Or you might want to write it in the form r cosine lambda times Dirac delta theta plus Dirac delta theta minus pi with some other constant. The problem is, how do you define the Dirac? How do you simplify products of Dirac deltas? It's not a problem about the coordinates, but how do you simplify products of Dirac deltas? I mean, you can come up with an algorithm,
And
but this, just give it a try, and obtain the constant is easier than trying to devise an algorithm.
and when we evaluate an integral over Dirac delta, shouldn't we substitute for the argument of Dirac delta in terms of some just one variable?
You can. I mean, Dirac delta has this property. You can either use this one, which is basically obtained by first identifying the values of x at which f of x is 0, then dividing your integration limit to a sum of around those points, and around each one of those points making a change of variable and defining u as your f of x. Sufficiently close to that point that change of variables will be 1 to 1, etc. You will be able to invert it.
So I can't directly take the integral over the left-hand side. I can't directly evaluate it. I have to make the substitution.
Well, this is again, the problem is, how do you define the Dirac delta of functions? So this is the definition. So directly taking the integral would be just using the definition of this Dirac delta. I would consider this directly evaluating the integral.
So
You can prove this property using substitutions, but once you know this property, it's direct evaluation of the integral of the Dirac delta. Okay, so see you next week. I'm waiting for your replies. Reply to the OTTE class in the forum so that your friends can also see, and we can all come up with a suitable date for the midterm.